Okie doke. Let's see. So, everybody's here, so that's good. I am recording these. I've been doing pretty well with this class. I've missed a couple of times with calculus. But I'm recording them just in case, one, you just want to go back and look at it. The other, just in case somebody is missing, but everybody's here today. Okay, so yeah, we're in this module 3. I got some grading done, you may have noticed. Does it alert you, or do you have to tell it to alert you, or something like that? I don't know. Does Blackboard say, hey, somebody posted a grade for you? No.
You get on Blackboard, it should give a notification.
Oh, okay. So when you get on Blackboard, but it doesn't like email you special or something like that. Okay. But anyway, so on your first project, you should be able to, at least if I understand it correctly, if you go to My Grades, you should find an attached document. You're nodding yes, so it must be true. You should find an attached document that has comments and the scores from the rubric on there, so you can kind of see where the points were. On the whole, people did quite well, so that was good. Made it through the couple of discussions, and you have 2 quiz scores up. Along those lines, I have added, and I'm not sure why I hadn't. I guess I just thought I had added these quiz items, but so. Yeah, if you go to quiz resources now, there are, at least at this point, 3 practice items. We'll talk about the Z distribution and confidence intervals today. And I'll try to get, I don't think I have any videos on that stuff, but I'll try to get some videos up. So a little behind on that, but it's also toward the end of the chapter, and although the calculation stuff with the Z tables, confidence intervals is important, I don't think from a conceptual point of view it's nearly as important as working on the project and trying to get through that and thinking about what all that stuff means, and how the normal distribution is used to help you finish that project. So, but we do have some calculation stuff in there, and if I can add some more soon, I will. Don't know if I'll be able to. I don't know how you all are doing, but I'm quite far behind, and that has very little to do with you and all that, and a lot more to do with just what I've been asked to do this semester. So, but we're getting there, and as I said, I got some grading done, so hopefully that'll help you, and I'll try to get to my next goal in this class is getting to your voice threads from Module 2 and voice threads from Module 3 then, to get on those so that we aren't far behind on getting you some feedback on that. So, okay, right at this point, any questions on anything? Nothing. Okay. I'm kind of used to that. I mean, it seems like people don't ask too many questions these days. Okay. Well, so we are, you know, we've talked a lot about the simulation stuff and all that in Chapter 2, a lot. We had an hour, or 50 minutes. But in the end, we don't use the simulation things. Now, for very complicated situations, actually, that may be what a person does, is they go to a simulation. I actually have a paper with a biologist from a previous life up in Michigan where she was looking at moth mating of all sorts of things. The reason to look at the moth mating was actually to control the moths. They were looking at mating behavior. And it's some type of gypsy moth, and they do a lot of crop damage, that kind of thing, I guess. And so she had observed, it appeared that the female would sit and send out pheromones, and hopefully a male would sense those pheromones and, you know, and find the female, and they would mate. But what she saw was if the female didn't attract a male within some amount of time, I don't even remember what it was now, it appeared the female would move, migrate, and try again. Well, that actually, you know, this is one of those things in biology, that actually went against what an earlier paper on their mating behaviors. And so the question was, well, would it be better to move around or better to sit there? And so we made a simulation. And we found that, statistically speaking, it was better to move around. And so that was why we had the paper. It was in the Journal of Theoretical Biology. And so, you know, we couldn't really answer that very well because it was too complicated a problem with just the kinds of statistical tests we have in here. We use those, but as part of the simulation. So, you know, it can get quite complicated in trying to answer some of these questions. So the simulation can come in, but as far as how we're using it right now, it's mostly about kind of setting up what's actually happening behind the scenes when we go to all these other tests and that sort of thing. So we have this thing. Oh, let me go back to this. Okay. So we have this thing called a normal distribution. And it's just a curve in mathematics. I mean, you know what a quadratic is, right? Ax squared plus bx plus c, right? And that has a particular shape and all that. Well, in the end, the normal distribution idea is it's just a function. And in its very simplest form, the standard normal distribution, it has a shape like this where it's centered at 0. Half the area is over here and half the area is on the right-hand side. And so this is a standard normal. And it has a couple of interesting properties about it. And it turns out this is what makes it so useful. Now, another reason it's useful is, well, lots and lots of things seem to behave with this type of distribution. So in other words, you know, here, whatever's tallest is where most stuff is happening, right? You just look at it as a bar graph or a histogram or something like that. You know, the highest frequency's in the middle, and the things that happen out at the end don't happen near as often. they're a lot less frequent. Well, lots and lots and lots of things that we observe in the world around us seem to have this kind of distribution where, you know, the most common things are all sort of lumped in the middle, and the least common things kind of spread out to either side, and they dwindle as they get farther and farther out. They're a lot less likely. And so it's very useful that way because it applies to lots of things. But it's also useful because it turns out, in many ways, this is the only one we need to know. Okay, we just need to know the standard normal. And it has some nice properties. So again, it's symmetric. So in the sense of being symmetric, right, if I want to talk about the area under here, now, and what we see with histograms and bar charts and so forth is, if I want to think of that area under there as everything that can happen, right? These are all the observations that made a given height here. You know, so think of it like a histogram. You know, I had observations in there, I had observations in there, I had observations in there, and so forth. That's all the observations that can possibly happen. Then what we see is, you know, and then the area is everything that could happen. We see that, well, half the area is on either side of 0. That's what the symmetry does for us. And that area is synonymous with the likelihood of something happening or the probability of something happening, however we want to say it, probability of it or likelihood. And then what we find out is, okay, so, it's fine. It's usually better if I try to draw the curve and then put the numbers under it. It never works well when I try to do it the other way around. So if you just look at a graph of this thing on the number line, and we look at it like that, then some other properties that we notice are that if I take the proportion of the area or the proportion of observations that are in here, okay, that's about 68%, okay, so 0.68. So of the whole population, about 68% of the area here, the proportion underneath this graph, is between -1 and 1. Okay? Well, then, if we go out here to -2 and 2, then in between there, so maybe I'll put some lines like that, then in between there, we get 95% or 0.95 of the population. Okay, and between -3 and 3, we get up to 99.7% or 0.997 in terms of a proportion. 99.7% of the population is in there. So I didn't draw it real great because it, you know, those look bigger than that, you know, than just 0.03. But almost all the population is between here and there. Now, you know, in the end, I think that would be a truly sort of a so what sort of thing, except those numbers, though, you know, they are numbers on the number line. They're just 1, 2, 3, and all that. But they are also, this is the number, each of these numbers along the number line, right, is the number of standard deviations for the population. So, you know, we talk about standard deviation. That comes up, and when you're taking some other class that uses data, and they'll say, what's the mean in the standard deviation, right? You know, always, what's the big deal with standard deviation and so forth? But you see, here, we're working with this normal distribution, and this is, I think, part of the reason that standard deviation is such a useful number, is that for the standard normal distribution, you know, this 1 corresponds to 1 standard deviation. This 2 corresponds to 2 standard deviations, okay, within that population. And so what this says is another way to view this number of spread, this standard deviation that we get, is that now, if I know it's a normal population, now that we're just looking at the standard normal, but it turns out it doesn't matter what normal distribution you're looking at. If you talk about things in terms of standard deviations, you always get the same answer. So if I just know something has a normal distribution, and I know I'm asking about, you know, what part of the population, what proportion, what percent of that population is between -1 and 1 standard deviations, I know the answer is 68%. Now again, you know, it's kind of weird because that's kind of exciting to me. Now why? Well, because I understand how powerful that is. You know, it allows us to then make all these other inferences that we make in this class. This, you know, it's a big deal. I realize I'm probably not going to get you really excited about that, you know, but it is a big, big deal that this is true. And so we want to kind of get that rule of thumb. So this idea here, they tend to just call this the rule of thumb, the standard deviation rule of thumb. Actually, let me see if I can. Here's the normal distribution in 2.6. So there they're showing the picture. There they're showing 2 different normal distributions. And they're saying standardized with the z-score, so we'll look at that in a second. But I am, somewhere in here they have their rule of thumb. I don't know. Probability examples. Yeah, well, I thought it was more at the beginning. I think they do it maybe toward the end. Here we go. There's their picture. Okay, so they have that 68%, 95%, and 99.7% in between the number of standard deviations. So mu is the mean, and sigma is the standard deviation. So there they have that picture, and you know, so they do like to point this out, and let's see, can I make that go away? Sort of. And I can zoom a little bit. Maybe, oh, here we go, zoom in. I don't know that that really worked very well. So, okay. so what they point out, SAT scores, you took the ACT, didn't you? Anybody take the SAT? No, okay. So up there, I'll put this on the board and then switch to the board, but SAT scores, it says closely follow a normal distribution. ACT scores do as well. With a mean of 1,500 and a standard deviation of 300, and I think that's actually changed now. So it may have, well, I don't know. I think for some reason I'm thinking the SAT scores have changed at some point. But so anyway, they tell us standard deviation of 300. And now more specifically, SAT had 3 different scores. Each had a maximum of 800, and 500 was the mean. And 100 was the standard deviation for each of the different areas. And so let me switch back to here for the moment. And so, let's look at SAT, and we'll just look at a single score. So SAT, I think it went from 200 to 800. And if any of you are considering taking the GRE, the graduate record exam, to get into graduate school, although a lot of graduate schools are beginning to not require that, it actually had the same scoring. I don't know if it still does or not, but it had this same type of scoring. So SAT for say you took the verbal or the math part, the quantitative part, or the writing part. Each of those parts had a score between 200 and 800, and so then with a mean of 500, so mu was 500, and sigma was 100, and so if you knew you got a score of 600, then actually you had a good idea of how you did. They would also give you the percentile, but so suppose I got a score of 600, okay, then approximately what that meant was that here's 500. We were out here at 600, which was mu plus 1 sigma. And from this picture over here, I can kind of come up with, really between the two pictures, I can come up with, how'd I do? Well, since this is symmetric, right, I could split that in half and say there's 0.34 on either side of the 0 there in the 1. So I know that in here was 0.34, or 34% of the population. And then over here, because it's symmetric, I know there's half the population over here. And so what that tells me is that a score of 600 I did better, because that's what I'm always interested in, right? Who did I do better than? I did better than 84% of those taking the exam. Now, if I got a 650, I'd have to estimate it's more than the 600, it's less than the 700. 700 right? You know, I could go to the 700 and say, well, okay, there's 95% in there. A half of 95 is what, 47 and a half. So 50% plus that 47.5%. If I got a 700, I was at somewhere around the 97.5th percentile, or you know, I did better than 97.5% of everybody. So if I was between 600 and 700, then I don't know, somewhere between the 84% and the 97.5%. So, you know, I don't have it exact, but it gives me some idea. And for that matter then, just to bring it home to something that you're a little more familiar with, ACT, that's more like a mean of 21 with a standard deviation of 5. Top score on the ACT, anybody remember what that is? 36. Notice what it is. It's 21 plus 3 standard deviations. 99.7%. If you get a 36, it says you're in the 99th percentile. So, you know, it works exactly the same way. I'm not sure what Lindsay Wilson says its average is. I don't know these days. You know, but again, if somebody tells me that they had a score of 26 on an individual portion or the thing overall, it works sort of either way. Oh, well, that's just like this, 84th percentile. All right, so 84th percentile there. Same idea, okay? Different scoring system, but it works exactly the same way. Now why? Well, partly because there's so many people taking it that you tend to get a normal distribution. Okay, now not everything behaves as a normal distribution, but a whole lot of stuff does. And in the textbook, they mention the central limit theorem. And this is actually the important thing here for us, because pretty much everything we look at are means. Even when we get into our chapter on analysis of variance, now variance is just the square of the standard deviation. That sounds like we're not talking about means anymore. We're talking about standard deviation or variance. But actually, the question it's asking in an analysis of variance is really, are the means equal? Okay, so sort of pretty much everything we do in this course is about averages or means. And the central limit theorem pretty much says that if we take a sample, okay, and find its mean, that is a random variable. You are seeing that in project 3. Okay, you sample, you do a simulation, you sample the numbers from 1 to 9, or wait, was that, no, that was 2, wasn't it? That was module 2. So in module 2, you took samples of 9 numbers, took their average, and it changed. It was a random variable. It wasn't the same every time you did it. But what you noticed was as you took bigger and bigger samples, the standard deviation or the variance of that mean got smaller and smaller and smaller and smaller. Okay, and if and when you looked at the picture, it looked a lot like these normal distributions. Okay, when you were looking at the means and sampling the means, getting the sampling distributions. And so what we find is as n, the sample size, gets large. Now, actually, it'll say something like goes to infinity or something like that. But just as it grows, as you get a bigger and bigger sample, oops, there we go. Oh, wrong place. There we go. As n gets large, so as n, the sample size, gets large, the sampling distribution of the mean gets close to normal. Now, a normal distribution, so it gets not normal like, oh yeah, that's what I expected, but normal as in the normal distribution, which I suppose is what I expected, but at this point. Now, this is actually quite amazing, okay, because this says, actually the central limit theorem says for any distribution. Okay, so if you take something like most light bulbs, at least now, I've never done the experiments to check this to see if it's really true, but I keep reading it everywhere that, hey, light bulbs, pretty much the life of a light bulb, its distribution or likelihood and so forth of how long it will last looks like this, right? There's 0. It can't last a negative amount of time, so it can't even be negative, right? But this is a light, a light bulb life population. Okay, its distribution, right? It just, it could go for a long, long time. It pretty much looks like this, I guess. Most electronic components, I guess, kind of look like this. That doesn't look anything like a normal distribution. Okay, it begins here, so it's only got one tail to one side, right? But if you were to go out and sample 1 million light bulbs and get their average life, what would happen is you would begin to see a picture, so 1 million sample means, well, no, 1 million sample size means, okay, so you get a sample size of 1 million, right? And you take their mean, and you just do that over and over. You might do it 1,000 times. You might do it 1 billion times. But But if you do that, but the sample size is 1 million, what's going to happen is that even though this can never be smaller than 0, it's going to end up doing something like that, which looks pretty much like a normal distribution. And that's kind of how the central limit theorem works, is even if you have something like this that cannot go left at all, because of taking all these samples, kind of what happens is you get this really narrow distribution, and you saw that in your module 2. You get this more and more narrow distribution. And well, if it's narrow enough, by the time I get to 0, there's pretty much no population to find there anyway. And so it would look like a normal distribution. It won't be exactly a normal distribution, but it'll be pretty darn close. And so you might as well call it a normal distribution. And so that's the idea of the central limit theorem, is that if you're looking at these sample means, in the end, for any reasonable size sample of actually any distribution, but certainly of most of the distributions we tend to look at, if you're looking at any reasonable size sample, you might as well assume you're looking at a normal distribution. Okay? And in your simulation, then that's, in this project, that's what we're trying to get you to also see, is that you are simulating these responses. Okay, so you're simulating these responses from doctors, but when you simulate them, what you're finding, right, is the African American, that was, they were around, what, 0.7 of like 30 some, 30, they had like 33 responses, I think, or something like that. So 70% of 33 is around 23 something. And so, when you did that simulation, we'll just call that 23, you should be finding frequencies that look like that. Well, looks like a normal distribution. And actually it is. It's really close to a normal distribution. It's even theoretically, it is not exactly a normal distribution. But it is close enough. And so, you're asking the question, in there, how likely is it I could be out there? Okay, because here's your data. Okay, and the way you have to do this in the beginning with the simulation is you have to run this thing 1,000 times, right? And so this is made up of 1,000 different observations of 33 responses. So it took 33,000 data points to make your picture. Okay, so you've got those 33,000 data points, and you get this picture, and then you had to, kind of figure out where this is, and then do a sum, and and decide, oh, out of those 1,000 observations, how many of them were here? And I don't remember off the top of my head, but I think you're getting somewhere around 8 or 10 or something like that. I don't remember for sure. But, you got out of 1,000, 1,000, you get 8 or 10, something like that. But it's more than, wait, 8 or 10? No, 80 or to 100, I think, because it's over 5%. I know that. So it's like 80 to 100. Okay, which is bigger than 0.05. Because 50 would be 0.05. And so we decide that, oh, okay, African American responses, we don't really have enough evidence to say they're different from responses on the whole. Okay, so we might believe they are. You know, actually, I would believe they probably are. But we don't have the evidence to say so, okay? Because we get a number that's bigger than the 0.05. And but this is a lot of work, right? And I don't make you do 257,000 observations for the Asian doctor group, right? Because there are, I think, 257 responses. And so if you did 1,000 lines of those, 257,000 different observations, that's a lot, right? I think I make you do like 1,000 lines, but it's not of 257 observations because I have you use the normal distribution. And see, with the normal distribution, if you can tell me the mean and the standard deviation, well, I can easily tell you what the answer is. Okay, so, you know, we've got things like spreadsheets. So if I tell you the mean is, we'll go with 23. All right, and we'll say, actually, I don't remember what the standard deviation is. So we'll just make something up. Standard deviation. And actually, it seems like I ought to be able to kind of guess it with the rule of thumb, right? Because, you know, my data ended up being at about the 90% mark. And so, and we know at one standard deviation, you're at 84%. You know, so maybe that's, you know, that was 1.5 standard deviations, and the data was, oh wait, yeah, I drew that wrong actually, because our data was the 23 or 24, and our mean was 50% of the 33 responses, so that was like 16.5. Yeah, the data was the 70%, right? Yeah, I think so. And, you know, so it was something like that. But it looks like, you know, somewhere around 6.5 or 7 units is the standard deviation, or is 1.5 standard deviations. So I don't know. I'll just guess at, you know, something like, say, at the standard deviation of 4. So if I have that, then what I can do is I can ask for, actually the problem is I can't ask for that number. I have to ask for that area. Okay, so I can ask the you know, I can look in the back of the book. I'll make a video on that. But I can look on something like a spreadsheet, and I can ask, you know, okay, how far is this? How far is it? That's a silly thing to say. You know, how much? What's the proportion of this thing, right? So, what's that proportion? But then, if I know the whole thing's 1 or 100%, I can just subtract. Okay, so here I can get the probability of being less than, oh, and see, I put that mean as 23, 16.5. What's the probability of being less than 23? And I just tell a formula. I say, well, I want a normal, so it's NORM dist, and I need my number, okay, my number is 23. The mean is the 16.5. Why did that go in there? Oh yeah, it did. Okay. And then my standard deviation. And then on older versions, you didn't have to put a 1 here, but I've gotten an email from at least one person who said they seem to have trouble if they didn't have the 1 there. So put a 1. And I do that, and it says, oh, you know, it's around 94.79. So I'm probably off a little bit on my numbers because I'm pretty sure you get something around 8 or 10% instead of just over 5%. But then I can get my p-value simply by, you know, my p-value is this area. Well, I just take 1 minus the area I found. So I'll say equals 1 minus that number. And I would get a p-value of actually right around 0.05 if these were the right numbers. In which case, you know, I wouldn't split hairs. You know, I'd just say, oh, yeah, not quite enough evidence. I might go that far if it was like 0.4 or 0.049, right? I mean, well, you go, oh, great, you know, we got a significant value is below 0.05. But in real life, I probably would say I need more evidence than that, you know. So, but it would be less than 0.05. It was 0.049. So, you know, it's fairly easy to calculate. If I just have the mean and the standard deviation and then the number I'm going for. And so that's the basic gist of these normal numbers. I don't have any videos there sitting for you right now, but I will make some videos on you know, all the different aspects of the normal distribution. So hopefully have that in a nice organized fashion for you to look at. And other than that, any questions right now on anything? No? All righty. Well, I will see you next Tuesday then.